All right, we're going to finish the exam 6 practice test. All right, so we did 1, 2, 3, and 7, so we'll do number 4. All right. So number 4, how do you make? We're trying to make 2 liters of 2.50 molar Ki. All right, so again, you have to know your units for capital M, molarity. So that is 2.50 moles of Ki per liter of solution. So it is moles per liter, moles of solute, Ki, liter of solution. And we want to make 2 liters of this solution. And so we need 5 moles of Ki. All right, so we don't have a balance that measures in moles. All right, and so we have to convert that to grams. So we take our 5 moles of Ki. We find the molar mass of Ki, which we did previously. That was in number 3, we use Ki as molar mass. It's 166. So periodic table, K 39.1, I 126.9, and we get a molar mass of 166 grams of Ki per mole of Ki. All right, and so when we multiply that, we get 830 grams. All right, so that is not how you make it, but you have to know that in order to make it. So to make a molar solution, you will use a volumetric flask. Whatever size amount that you need, that's the size volumetric flask. So we need a 2-liter volumetric flask. All right, so we're going to put in, let's say we're going to add 1.5 liters of water. And then we're going to then dissolve the 830 grams of Ki. All right, so you're going to put in your 1.5 liters of water, then you're going to put your 830 grams of Ki. You're going to swirl it until all of the Ki dissolves. Once all of the Ki dissolves, then you're going to add water until you reach the 2.000 liter mark. All right, so a volumetric flask has 1 mark on the stem, and so it is the 2-liter mark for a 2-liter volumetric flask. All right, so when you're done, you don't know exactly how much water you put in, but you know that your final solution, because it is liters of solution, the water plus the Ki is going to be 2 liters. It doesn't matter. You have to have enough to dissolve it, but you don't want to add too much. You cannot go over the 2-liter mark. So if you want to do 1 liter and dissolve it, maybe that's not enough water. Fine, just add more water until it all dissolves. And then once it's all dissolved, then you add more water until it's at the 2-liter mark. But 830 grams of Ki, that's a lot of Ki. All right. All right, so now in part B, it says we want 20 grams of Ki. All right, so we need 20 grams of Ki, but now all of our Ki is gone because we used all 830 grams of it, and we made a 2.5 molar solution. All right, and so now I need to know what volume of this 2.5 molar Ki do I need to add to get the 20 grams of Ki. All right, so we have 20 grams of Ki. We are going to convert that into moles. So we have again 166 grams per mole of Ki. Now, once we have our moles of Ki, we can then use our molarity, which is 2.50 moles of Ki per liter of solution. All right, and so we can then convert that to milliliters. It just asks for a volume. I'm going to get this in milliliters, so I'm going to get rid of my liters by having liters on bottom, and I want milliliters, and M is 10 to the minus 3. So again, you can put the 1,000 milliliters per liter. I will have my M on top, and I will have that minus 10 to the minus 3 on bottom. All right, and so when you push the buttons, you get 48.2 mils. So if I take 48.2 mils of 2.5 molar Ki, that will be exactly 20.0 grams of Ki. All right. So make sure you know your units for molarity, moles of solute, liter of solution. Number 5. All right, so we have a solution that is H2C2O4. All right, so we have made aqueous H2C2O4. All right, so this is an acid. Anything that starts with H is going to be an acid. This is not one of the 6 memorized strong acids, and so it is a weak acid. All right, so you have to still know the 6 strong acids. That is not one of them. That means it is the weak acid. So remember, when you do your net ionic equations, when you have a weak acid, it stays together. If you have a strong acid, it breaks into ions. All right, so this is important now because this is going to stay together. And anytime you stay together, your I value is 1. But if we had HCl, that's a strong acid, and then your I value would be 2 because it is going to go to H plus and Cl minus. Only the strong acids will have a I value greater than 1. All weak acids, your I value is 1. All right, so we want to find the concentration and molality. So it says that I have this solution, and I did my experiment. I added it to salt water, and I measured the freezing point. And the freezing point of this, well, salt water and ice salt to lower the temperature, and it did freeze, and it had a freezing point of minus 1.80 degrees Celsius. All right, so it's aqueous. That means it's in water. And so we did a freezing point. And so we have our delta T sub F is equal to I Kf C sub M. All right, and so your C sub M is concentration in molality. Your delta T sub F is how far the freezing point went down, freezing point depression. It went down by 1.80 degrees Celsius. So water by itself would be 0. Now it's at negative 1.80. So the delta T sub F, the freezing point depression, it went down by 1.80 degrees Celsius. Weak acid, the I value is 1. Kf is a constant. You look it up. 1.86 degrees Celsius per molal. And you just solve for your concentration in molality. All right, so you divide both sides by the 1.86, and you get your C sub M is equal to a 0.968 molal. All right, so now that we have the molality, then the question is, well, then what is the boiling point of this solution? All right, so the boiling point you would find by delta T sub B is equal to I Kb C sub M. All right, so you are now calculating your boiling point elevation. The I value for the weak acid is 1. Kb, you look it up. It's a constant. 0.512 degrees Celsius per mole. And the concentration of this weak acid, we just calculated right there. The concentration in molality is 0.968 mole. And so your delta T sub B is equal to 0.495 degrees Celsius. All right, but it didn't ask for the freezing point depression or the boiling point elevation. It asked for the boiling point. So the boiling point is not 0.495. That's how much it went up. It's water. Water has a boiling point of 100. And so it went up by 0.495 degrees Celsius. And so the boiling point of this solution is 100.495 degrees Celsius. So make sure you're answering the question. If they ask for the boiling point, it's 100.495. If they're asking for the boiling point elevation, it is 0.495. All right. So in part C, it asks for the mole fraction. So let's find the mole fraction. We'll find it of both of them. So we're going to find the mole fraction of the H2C2O4. And when we're done with that, we will get the mole fraction of water as well. All right, in order to find the mole fraction, we need to find the moles of the H2C2O4 and divide by the moles total. So that means the moles of your H2C2O4 plus the moles of water. All right, and so you need to know the units for little m. If you know the units for little m, then this is not a hard question. If you don't, it's an impossible question. 0.968 moles of solute. The solute is the weak acid, H2C2O4. Per kilogram of solvent. The solvent is water. All right, so we already have our moles of H2C2O4. It's right here, 0.968. And so we already have those two, 0.968. 0.968. Now we just have to find moles of water. We have a kilogram of water. All right, and so a kilogram of water, that is 1,000 grams of water. And we divide by the molar mass, 18.02 grams per mole of water. And so then we have our moles of water. So I'm just going to put in here, you take 1,000 divided by 18.02. And this is going to be your mole fraction of your weak acid. So the mole fraction of the H2C2O4, when you push the buttons, is 0.0171. And so if you wanted the mole fraction of the water, you could then put this in the numerator and push the buttons. But the easiest way to do it is know that they have to add up to 1. So 0.9829. would be your mole fraction of water, because when you only have two things, the mole fractions must add up to 1. If you're doing percents, they must add up to 100%. All right, so that is number 5. All right, number 6 is a multi-part question again. So, number 6, calculate the vapor pressure of water at 35 degrees Celsius. So we want to find the vapor pressure of water at 35 degrees Celsius. All right, and so they do give us a bunch of constants. The one we need, delta H of vaporization. That is 40.7 kilojoules per mole. All right, so we have to use the Clausius-Clapeyron equation because we know the normal boiling point of water Normal means 1 atmosphere. So if you go to Denver and boil water, it's not 100, it's 95, or depends on the pressure of that day. But the normal boiling point is always 100 degrees Celsius because normal means 1 atmosphere. All right, so we always have the boiling point of water at 1 atmosphere. That is 100 degrees Celsius. All right, so we can use the Clausius-Clapeyron. The natural log of P2 over P1 is equal to your delta H of vaporization divided by R. 1 over T1 minus 1 over T2. That equation is given on the test. All right, you have to have all of your temperatures. Anytime you have T, it has to be in Kelvin. Do not use 100. It is 373.15 Kelvin. Do not use 35. That is 308 Kelvin. You're adding 273.15 in order to get your temperatures in Kelvin. All right, so your T1 here is equal to 373.15. Your P1 is equal to 1 atmosphere. Your T2 is 308 Kelvin. Your P2, that is the thing we're going to solve for. All right, so the ln of P2 over 1 atm. Now, note the units for the pressure, they just have to be the same. Since we're using atmospheres, when we get our answer for P2, it's going to be in atmospheres. If you put 760 millimeters of mercury here, which is fine, then your answer for P2 would be in millimeters of mercury. All right, so your delta H of vaporization, 40.7. We don't want kilojoules because we have 8.314 joules per mole Kelvin for our R value. So this has to also be in joules per mole. So I'm going to get rid of my K because I know K is 10 to the third. So instead of putting the K in, I'm putting times 10 to the third joules per mole. So it is 40.7 times 10 to the third joules per mole. So that my joules per mole cancel my joules per mole. 1 over T1, 373.15 minus 1 over T2, 308. All right, again, these must be in Kelvin. If it's a multiple choice, the answer, if you put Celsius, is there. It is the wrong answer. Always temperature in Kelvin. All right, so now we have the ln of P2, and then we do our parentheses first when we solve this. So we're going to do our parentheses first, then multiply it by the 40.7 times 10 to the third, then divide by 8.314, and you will get negative 2.77. All right, and so then to get rid of the ln, you got to push your e to the x button on your calculator. ln is the natural log, so that is base e. You have to push your e to the x button. E to the ln, that just goes away. You got P2, e to the negative 2.77. That is 0.0627. And that is in atmospheres because we put P1 in atmospheres. So whatever you get for P2, that is the unit, atmospheres. Many times for vapor pressure, they're going to ask for millimeters of mercury. So to convert that to millimeters of mercury, there are 760 millimeters of mercury in 1 atmosphere. And so P2 is 47.6 millimeters of mercury. All right, so both of these answers are exactly the same. Doesn't matter which one you pick unless it says give your answer in millimeters of mercury. Well, then you have to put it in millimeters of mercury. All right, part B. Part B is find the pressure of this solution. Calculate the vapor pressure of the solution at 35 degrees Celsius. All right, and so that solution is in the question. We added 20.2 grams of glucose, C6H12O6. We dissolved that in 125 grams of water. All right, so that is how we made our solution. Now we want the vapor pressure of that solution. So at 35 degrees Celsius, we have the pressure of water in millimeters of mercury. It's right here. Now we made this solution and we want the vapor pressure of this solution. So you have a boiling point elevation, you have a freezing point depression, you also have a vapor pressure lowering. All right, and so that is your delta P, is a vapor pressure lowering. All right, so there's going to be two equations given, one with the delta P. So the delta P is equal to your mole fraction of your solute, in this case, C6H12O6, times the pure pressure of your water at that temperature, which we calculated, 47.6 millimeters of mercury. You're also going to be given that the pressure of your solution is equal to the mole fraction of your solvent, which is water, times the pure water. All right, so you have both of these equations, and you can use either one of these equations. So in part B, it asks for the pressure of the solution. So I'm going to use this one. I could calculate delta P and then lower it from the P2, which is what we calculated in A. That would give you the exact same answer. I'm going to use this one because it's going to go right to my answer and I don't have to do anything else but circle it. So my pressure of this solution is the mole fraction of water. To find the mole fraction of water, I got to take the moles of water, divide by the moles of water, plus the moles of the sugar, C6H12O6. All right, so I'm given a mass of both of these. So I got 20.2 grams of glucose. I got 125 grams of water. And so I just convert grams into moles by dividing by the molar mass. All right, so moles of water. I take 125 grams of water, and I divide that by the molar mass, 18.02 grams per mole. And that is going to be my moles of water. And that is 6.94. All right, in order to find my moles of glucose, I take my 20.2 grams of my C6H12O6, and then I look to the periodic table, get the mass of 6 carbons plus 12 hydrogens plus 6 oxygens, and that molar mass is 180. And so the molar mass, 180 grams per mole. And so when I get my moles of my sugar, it's 0.112. All right, so then I just plug it into the mole fraction of water equation. So that is moles of water, 6.94, divided by moles of water, 6.94, plus the moles of the glucose, 0.112. All right, and so when I push that on my calculator, I get a mole fraction of 0.984. All right, and so if I wanted the mole fraction of the sugar, so we can do that one, mole fraction of the glucose, C6H12O6. I take my 0.112 and then divide by the 6.94 plus the 0.112. And that gives me a 0.0159 for the mole fraction. So the mole fraction of water, 0.984. The mole fraction of your glucose, 0.0159. And when you add that up, that has to add up to 1. But sig figs here are 0.999, so it's a bunch of 9s, which would round to 1. All right. So now we can solve our question here. So we wanted to know the pressure of the solution. And that's the mole fraction of the water times the pure water, water without anything in it. And that's what we solved for in the first part. Part A was find the pressure of water at 35 degrees Celsius. And that was 47.6. So we know this is 47.6 millimeters of mercury. We now know the mole fraction of water. We just solved for it, 0.984. And now that's the pressure of our solution, which has to be lower than the pressure of water. There is a vapor pressure lowering, and so it is. So the pressure of this solution, when you push the buttons, is 46.8 millimeters of mercury. All right, and so part C is calculate the vapor pressure lowering, delta P. Well, that's the mole fraction of your C6H12O6, your sugar, all right, times the pressure of pure solvent. And we have that number 2. Right there, we have the mole fraction, which is 0.0159. And we have the pressure of pure water, that's the 47.6. And that will give us our vapor pressure lowering, which is 0.757. All right, so you have your pressure of your solution, and it lowered it by 0.757. And part D. Part D, find the freezing point of this solution. All right, so we need our delta T sub F. And that is equal to I Kf C sub M. All right, and so your I value for any molecular compound is 1. So if you have an ionic compound, it is going to be greater than 1. If you have a molecular compound, it is always 1. All right, so sugar is a molecular compound, no metal with a nonmetal. We have I value of 1. Kf is given 1.858 degrees Celsius per mole. That's given in the problem. And now all we need to do is find out what the molality is. And again, this is impossible unless you know the units for molality. So your C sub M, molality, we need moles of solute. And we then need to divide that by kilograms of solvent. So it is not solution here. Molarity is moles per liter of solution. Molality is moles of solute, kilograms of solvent. All right, so we have to find moles of solute. The solute, we use 20.2 grams of our C6H12O6. So to get moles, we divided by 180 grams per mole. We already did this. And we got our 0.112 moles. All right, and we now have 125 grams of water, but we don't want moles of water this time because we need to convert our grams into kilograms of this solvent. So we don't want grams, we want kilograms, and we know kilo is 10 to the third. And so we're dividing by 1,000. And so that is a 0.125 kilograms of water. All right, so the moles of the solute is the C6H12O6 divided by kilograms of solvent. The solvent is water. And so you get your molality by taking the 0.112 moles divided by your 0.125 kilograms. And that gives you a 0.896 molar. Molal. All right, so that's 0.896 molal solution. So there is your molality. So now we can get our answer. So again, our delta T sub F is equal to I Kf C sub M. Now we have our C sub M, concentration molality, 0.896. So our delta T sub F is equal to our molecular compounds. All molecular compound I value is 1. Kf given 1.868 degrees Celsius per molal. And now we have our 0.896 molal solution. So we push the buttons on the calculator and we get 1.66 degrees Celsius. All right, but that is not the freezing point. That is the freezing point depression. So delta T sub F is not the freezing point. It is the freezing point depression. And so the temperature of freezing here is negative 1.66 degrees Celsius. It went down 1.66. The freezing point of water is 0. So it is negative 1.66 degrees Celsius. All right, and so also in that same part D, it says, what's the boiling point? So delta T sub B is equal to I Kb C sub M. Delta T sub B, again, sugar, molecular, 1 is your I value. Kb is a constant given to you in the problem, 0.512 degrees Celsius per molal. We already calculated the molality. It is the 0.896 molal. So our delta T sub B, when we push the buttons, is 0.459. So delta T sub B, 0.459, except that wasn't the question. The question wasn't what is the boiling point elevation. The question was, what's the boiling point? So the temperature of boiling, it went up by 0.459. The boiling point of water is 100. And so now it is 100.459 degrees Celsius. All right, part E. Part E says calculate the osmotic pressure. This equation is also given. That is your IMRT. All right, so here you have to know that osmotic pressure is going to be in atmospheres, which tells you what R value to use. So you have to use the 0.08206 liter atmosphere per mole Kelvin. All right, and of course, as always, your temperature has to be in Kelvin. All right, and so we're at, again, 35 degrees Celsius. And so that is equal to 308 Kelvin. So we have our R value. We have our temperature value. I, again, is 1. It is a sugar molecular compound. Now we got to find our molarity. By far the hardest thing to do is then to find your molarity. In order to find it, you have to know the exact units. So molarity is moles of solute per liter of solution. All right, we've done moles of solute a bunch of times, so we know that that's the 20.2 grams divided by the 180 grams per mole. So we have the 0.112 moles again. So we have that. We know the moles of our solute. So the question here is not that. The question is, how do we find the liters of solution? So this one is much more difficult. All right, so what we did was we took our 20.2 grams of our solute, C6H12O6, and we had 125 grams of water. And so then we mixed those together and we got 145.2 grams of this solution. All right. So we have the grams of solution. We don't want grams of solution. We want liters of solution. Well, in this problem, the density is also given. And this is where we finally use the density that is given. So the density in the problem says it's 1.10 grams per milliliter. You must know that units for density. All right, so just like molarity, mole solute, liters of solution. Density, grams of solution per volume of solution. So it's the mass of solution divided by the volume of solution. It's both solutions when you're doing density. All right, and so since we have the mass of solution, 145.2, and we have the density, we can then convert that into volume of solution. So we have 145.2 grams of solution, and we have the density, which is 1.10 grams of this solution per 1 milliliter of this solution. But again, for molarity, we want that to be in liters. So we need to get rid of the milliliters and get liters. And m is 10 to the minus 3. And so when you do that, you get a volume of 0.132 liters. So there's our volume of solution. And here is our moles of solute. We just divide those two numbers. So the molarity is 0.112 moles of your C6H12O6 divided by your 0.132 liters. And that gives you a molarity of 0.850 molar. All right, and so now we can solve for the osmotic pressure. So osmotic pressure is IMRT. So osmotic pressure 1, now we have the molarity, 0.850 moles per liter. R, 0.08206 liter atmospheres per mole Kelvin. And 308 Kelvin is our temperature. So the Kelvins cancel, the moles cancel, the liters cancel, and we are left with osmotic pressure in atmospheres, which is 21.5. All right, then part F. Part F is basically writing down all the things that we just did, except for the first one. The first one wants the mass over mass percent, or it could just simply ask for the percent because unless it is something other than mass percent, it's usually not listed. So all percentages are mass unless it says otherwise. All right, and so that's part over whole times 100. And we had 20.2 grams of our C6H12O6. We had 125 grams of our water. And so the whole was 145.2 grams of this solution. So to get your mass percent of your sugar, you take your 20.2 grams divided by the total, which is 145.2. To get a percent, you multiply by 100, and so that is 13.9 C6H12O6. And all the other ones we already did. And so you just look above when we found our mole fraction of our C6H12O6 and write down that number. That number was 0.0159. It asks for the molality. So again, we already calculated the molality. It is 0.896 molal. And it asks for the molarity, which we just calculated. And that is a 0.850 molar. All right, so we already calculated the mole fraction. We already calculated the molality. We already calculated the molarity. All right, so it's just asking for those numbers. All right, that is the end of the practice test.